Hello everyone. In the second lecture of the physical chemistry chapter Specific Heat of Solids, Dulong Petit's law will be discussed. So what is the Dulong Petit's law? It was suggested by Dulong and Petit in the year 1819 from some experimental data. And their law states that the atomic heat means the actually molar heat also. That means specific heat into atomic weight. So at the atomic heat or molar heat capacity, that is C or Cm, of all solid elements is a constant quantity and is approximately equal to 3R or 5.9 calorie per Kelvin per mole, or in the SI unit it is 24.9 joule per Kelvin per mole. So they have suggested that all the solids, maybe it is metal, maybe it is non-metal, all the solids have the heat capacity C or Cm. Initially, it was found to be 6.4 calorie per Kelvin per mole. But after some correction, it was found that it is nothing but equal to 3R or 5.9 calorie. Okay. So why the correction or what type of correction took place? We must discuss it, but later on. Look, initially, the experiments were carried out at constant pressure. And in that case, this, this heat capacity, molar heat capacity, since it was derived in the constant pressure condition, so it was nothing but Cp. Okay, and Cp was found to be equal to 6.4 calorie per Kelvin per mole. Now we have the expression Cp minus Cv. Just we derived it in our previous lecture, that is lecture number 1. This difference Cp minus Cv is Tv alpha squared by beta T. Alpha is thermal expansion coefficient, beta is compressibility coefficient isothermally. So with the help of this equation, Cp was replaced by Cv. So some value was deducted from the value of Cp and it was reduced from 6.4 to 5.9. So Cp was replaced by Cv, resulting in Cv equals to 3R, and this is simply the Dulong Petit's law. But this law, do you think this would be applied for all types of solids? All the solids are not having the same crystalline character, because if some are purely metal, then some are non-metals also. Some are in the atomic state, but some are in the molecular. Suppose if you take ice is completely in the it's a molecular crystal. Whereas if you take suppose iron, it is metallic crystal. If you take sodium chloride, it is ionic crystal. So there are different types of solids are there. So there must be some disputes in this law, but the credit of Dulong Petit is that they have first observed this property. So the law holds good in case of metallic solid and they are very good at higher temperature. But the law fails in case of the non-metals such as diamond, graphite, silicon, beryllium, boron, etc. And at a very low temperature, that is in the cryogenic level, near absolute zero, that is 100 Kelvin or maybe 150 or 200 Kelvin, this law does not hold good. Now let us see the experimental results. Look, in case of thallium up to 50 Kelvin, this value is almost equal to 5.9 calorie. In case of lead, this value just near about 120 to 130. This value is good. In case of aluminium, at this position, that is nearer in the room temperature, 300 Kelvin, the law holds good. But at lower temperatures, this law fails. That is, it is very much lower than 5.9 value. And in case of non-metals, definitely, whatever be the temperature, maybe it is lower or higher temperature, or in case of diamond or whatever it is, it does not show some good agreement with the experimental result 5.9. So let us derive this equation theoretically. So in 1 mole of a crystalline lattice, there are how many atoms? Na, Na number of atoms. And they are associated with only vibrational motion. There is no translation, there is no rotation. But we know this vibration has two types of modes, that is potential energy and kinetic energy. So each atom is contributing energy in two modes, such as the kinetic energy and the potential energy. And each mode has three axes, that is 3 degrees of freedom. This one, kinetic energy along x-axis, kinetic energy along y-axis, kinetic energy along z-axis. Similarly, potential energy along x, along y, and along z-axis. That is, there are 2 into 3 number of degrees of freedom. So from the theory of principle of equipartition of energy, now each quadratic degree of freedom, that is, suppose kinetic energy along x-axis, this is one quadratic degree of freedom. And what is its value? According to this principle of equipartition of energy, this value is half kT. So the value should be 2 into 3 into half kT. Now how many atoms are here? In a number of atoms. So overall energy, in order to determine the overall energy, this overall thing will be multiplied by Na. So what is the value of uh, total energy? Now the total energy U, 2 into 3 into half K2 into Na. Okay. And here half K is nothing but the Boltzmann constant, and Na is the Avogadro's number, and T is the temperature. So why 2? 2 for 2 out of 2, 1 for potential energy, another one for kinetic energy. So 1 plus 1, 2. Now each mode has 3 axes, 3 degrees of freedom. So for x, y, and z, this is 3. Half kT, each quadratic degree of freedom, it has the energy form, half kT. And overall number of atoms is Avogadro's number for one mole, that is Na. So the overall energy has expression 2 into 3 into half kT into Na, that is 3 kT into Na. Now we know that K into Na, Boltzmann constant into Avogadro number is universal gas constant R. So K into Na, in place of this, we write here R. So it becomes finally thrice RT. Now what is the expression of Cv? The Cv has the expression del U by del Tv. And we have got the value of U, theoretically, it is equal to 3RT. So just differentiate 3R2 with respect to T at constant volume, and it gives the result 3R. So Cv equals to 3R. It has been proved. And this is known as the Dulong Petit's law. So that's all about the second lecture. Thank you and have a nice day.